Bismillahirrahmanirrahim and Assalamu alaikum. So we're going to do first of all a very quick recap of the interaction free measurement. All right, so can I start? All right, so let's look at our Mach-Zehnder interferometer again. A beam splitter. Let me do the usual thing of drawing a box. The beam splitter, the perfect mirror, the second perfect mirror, and another beam splitter. And our two detectors, D1, D2. A photon comes in, takes the horizontal path using the path degree of freedom as our quantum state, and if we adjust the arm lengths properly so that the path length difference between the two arms is exactly 0, then the probability of detection on D1 is 1, the probability of detection on D2 is 0. All right, so this is our output port cat 0, this is the output port cat 1. All right, so far so good, and we've already seen the progression of the quantum state through this interferometry, and now we have a fair amount of belief that this is going to happen. We know that it happened in the experimental laboratory, and we now have a kind of consistent self-coherent description of why this happens. In the next stage, we modified this simple Mach-Zehnder interferometer and placed an obstruction in one of the paths. So let me redraw the interferometer here. Our beam splitter, number 1, first mirror, second mirror, the second beam splitter, and once again our two detectors, D1 and D2, and in this path we've placed an obstruction, and the photon once again comes in the path cat 0, and now we observe that there are three possibilities. This is an absorbing material. Whenever a photon strikes it, it absorbs the photon, and the photon just vanishes, it is annihilated, it disappears, it's destroyed totally. And when the photon is destroyed, neither of the detector can click. So there are three possibilities. Now let's look at the three possibilities. They are the following. One possibility is that no detector clicks, and we've already seen that this probability is 1/2, because if this were an absorbing object, a single photon comes in, and if you look at the probabilities of taking this bottom path, let's call it path 1, let's call this path 2. The probability that the photon takes path 1 is 1/2. So the probability that neither of the detector clicks because the photon has already been absorbed in path 1 is 1/2. So this probability is 1/2. The other two scenarios are that D1 clicks or D2 clicks. Remember, both of them cannot click at the same time because the photon is indestructible, it cannot be split. So the second possibility is that D1 clicks. Now since 1/2 is the probability that neither of the detector clicks, the probability that a photon is eventually discovered on D1 or D2 is 1 minus 1/2. So it's 1/2. So now there's 1/2 probability that either of the detector clicks. Now there's no distinction really between the two detectors, So the probability that D1 alone clicks is 1/2 of 1/2, which is 1/4. And since the probabilities need to be conserved, the probability that D2 clicks is 1 minus all of this is 1/4. Now in this perfectly balanced interferometer, this is a perfectly balanced interferometer, and I say it's a balanced interferometer because the two path lengths have been finely adjusted so that the path lengths are equal, which means there is no distinction between the two paths, which means we do not have any which path information, which means that interference is possible here. So here interference does take place, and interference does take place means that this output channel this is where the two kind of waves recombine constructively, and here is where the two waves recombine destructively, so that this remains dark whereas this remains bright always. So there is this possibility of interference here, and interference does take place here because we do not know which path the photon has taken. We are completely ignorant of the which path information. We do not have any knowledge of the path of the photon. And since we do not have any knowledge of the path of the photon, we are totally uncertain about it. We can be certain about the momentum, which means that we can see interference fringes, which means that we can see interference unfold here, giving a bright channel here and a dark channel here. Got it? Now in this case, if either of the detector clicks, we know that that photon must have taken path 2. Otherwise, you wouldn't see a click. So clicking, the outcome of this experiment is revealing that we have information about the path of the photon. So when we have information of the path of the photon, we cannot be certain about the momentum, which means the momentum is uncertain, which means the direction the photon takes at this output port is totally uncertain, which means either of the two detectors can click. So far so good. Yes, one or two questions. Yes, please.
So, if we only put one photon in the first process, the first one.
Here?
Yes. So then how would they interfere destructively if there's only one photon?
Well, they do. So one photon, that's what we've been talking about in the past 2 lectures. A single photon can interfere with itself. All right? Yes, please. No? So here, in fact, so what is an interference pattern? Bright and dark fringes. So bright areas, dark areas. This is our bright area and this is our dark area. That's why I call it interference. In this case, I will explain later that even at one output port, you can see on a screen fringes because you're never able to get these precise pencil sharp beams. The beams diverge. When they diverge, you get a range of path differences. You can actually see fringes if you put a screen at one of the detectors, but I'm going to come to this point later. So this is here, in this case, is which path information available? In this case, no. We do not know which path the photon has taken. Single photon, just one photon. Whereas, therefore, do we see interference? Yes. In this particular example, the which path information is available, and we do not see interference, which means both of the detectors can click. All right, now let's kind of come to this question again of, yes, please. So here this obstruction has collapsed the superposition right inside the interferometer. So the interferometer is really not acting like an interferometer here. You have pried open the interferometer and put an obstruction here, and the wave function has collapsed, or the quantum state has collapsed right here. You have no superposition, it's already collapsed. Here, the superposition persists, and it persists in such a fashion that you collapse the superposition after the interferometer. Yes, please.
अगर D1 या D2 में से कोई भी नहीं करता तो we know for sure कि it is second path one.
Of course. In this case? Of course, because the photon has to go somewhere. Even though it's an ideal experiment, it could be lost to oblivion, but we assume that it goes somewhere. Yes, please.
And I just wanted to clarify, we are more certain about the probability of D2 over D1, right?
Here, in this case?
Yes.
Why?
Because like a path one.
So, right. Why? So, it's the photon is coming in through this state. It's in the state ket 0 here. Here, a superposition is created of ket 0 plus 1, equal coefficients, equal probability amplitudes. You take the modulus square, you get 1/2. D1 and D2 have no mutual preference. They are equiprobable. Yes, please.
So in the second case, we can say that which path information is the measurement that collapses the superposition.
Yes. All right, so now a slight dramatic twist, as I mentioned in the previous. Suppose I have a bomb and I place the bomb here. This is my bomb, and it's triggered by a single photon. So now we've placed a bomb inside this path, and there are two kinds of bombs, a good bomb and a bad bomb. A good bomb is such that when a single photon hits its trigger, it just explodes. And a bad bomb is one that even it does not detect a photon, which means the photon goes unscathed or just passes through this trigger and the bomb does not explode. So now you have a collection of bombs. The trigger is so small that you cannot observe them visually, but you have single photons at your disposal, and you want to test whether a bomb is good or bad. So classically what you would do, you would fire a photon onto it. If it explodes, it's a good bomb. If it doesn't, it's a bad bomb. So in order to detect the presence of a good bomb, it must explode, which means you must observe it. This means that it's impossible to detect a good bomb without having a photon shine on it. It must interact with the photon so that you can tell whether it's a good bomb or a bad bomb. Now in this kind of interferometric experiments, you can tell whether a bomb is good or bad even without a photon interacting with it. Now this is totally non-classical. You cannot do this in the classical world that we normally live in, but we can do it in the quantum world. So you can observe something without light interacting with it. You can observe something, you can observe or get or see something without looking at it. See something without looking at it. Kind of counterfactual. So now it's exactly the same argument over here. Now there's a bomb here and you want to test whether it's good or bad. And you want to find out a good bomb without the photon interacting with it. That's why it's called an interaction-free measurement. So let me draw this interferometer again. Beam splitters, mirrors, mirrors, beam splitter. D1, D2. Now I know that first of all I balance my interferometer. Before I put the bomb inside one of the arms, I balance it. Balancing it means that the first scenario is achieved. D1 always clicks and D2 never clicks. So I have balanced my interferometer before I start the experiment. Then I place my bomb. So there is a bomb inside one of the paths. That's given. There is a bomb inside one of the paths. And if the bomb, so there is a bomb. First of all, there is a, so I'm building up the quantum logic here. There is a bomb. I know that because I put the bomb inside the interferometer myself. There is a bomb. I want to check whether it's good or bad. And I want to do it in an interaction-free kind of technique. So there is a bomb, and if the bomb absorbs a photon, it explodes, because it must be a good bomb if it absorbs a photon. A good bomb absorbs a photon and explodes. So an explosion means, if I just have a bomb and it explodes when it sees a photon, it means that the photon has been absorbed and it's a good bomb. Okay, so whenever the photon is absorbed, which means whenever a photon is subtracted from the system, so I shine a photon and if it just disappears, it means it has been absorbed by the bomb, which means it must explode, it means it's a good bomb. So explosion implies it's a good bomb and the photon has been absorbed. So this is given to me. Now once again there are three possibilities. Does not absorb a photon. The photon just passes straight through the trigger. Let's see. So if no photon is observed either on D1 or D2, it means that the photon has been absorbed. So I'm shining in a single photon into the system. The path is my quantum degree of freedom. I shine in one photon. Now this photon comes in and neither of the detector clicks. I've already seen that there's a probability that this happens, which is 1/2. Now if neither of the detector clicks, the photon must have been absorbed inside the interferometer, and the only way it can be absorbed is by the bomb, which has therefore exploded. So the probability that none of the detector clicks is 1/2, 50%, and this is when we know that the bomb has absorbed the photon and an explosion has taken place, and therefore it is a good bomb. So if this happens, which happens with the probability of 1/2, the bomb is good and an explosion has taken place. So this is telling you that the bomb is good. But you can also do this classically. You can shine a photon on a bomb standing on its own. If it explodes, it's a good bomb. So there's nothing quantum mechanical about this. It doesn't give you any kind of clever insights. All right. So now the second probability is that detector D1 clicks. All right. Now the probability that detector D1 clicks, since this is half, there's half probability that the detector D1 or D2 clicks, and there's an equal probability that either of these detector clicks. So the probability that this happens is 1/4, just as we've seen before. But if the detector D1 clicks, there are two scenarios. One is that the bomb is kind of bad, and if the bomb is bad, the single photon is in a superposition here, it's not impacted by this bomb, and it just gives a click on D1. So the bomb could be bad, but it's also possible that the bomb is good, right? So if the bomb is good, then we would say that, all right, since the probability of and there is no explosion, which means you could infer that we've detected a photon, so it hasn't been absorbed by the bomb, but the bomb is there. So if this probability is 1/4, then there can be two likelihoods in this scenario. One is that the bomb is bad. If the bomb is bad and you place the bomb inside the interferometer, if the bomb were bad, this will act just like a balanced interferometer, and there's some likelihood that D1 is going to click. So it has clicked. So the bomb could be bad, but the bomb could also be good, right? So it's possible that the bomb is good and the photon has not interacted with the bomb. So I'll come back to this point in a minute. Let me finish my complete argument. All right, so what about the probability that D2 clicks? Now in a balanced interferometer, this probability were 0. Now it appears that this probability has now changed from 0 and it's become 1/4. All right. If this happens, detector D2 clicks. So look at the kind of sequence of my arguments. D2 clicks, which means the photon is detected by D2, which means that the photon has not been absorbed by the bomb. All right. Now we want to decide whether it's a good bomb or a bad bomb. If it were a bad bomb, then the probability that detector D2 clicks is 0. Therefore, it must be a good bomb. So now if detector D2 clicks, which happens 1/4 of the times, if it clicks, if detector D2 clicks, we can infer with certainty that the bomb that has been placed inside this interferometer is a good bomb. No explosion has taken place, and still we can say that the bomb is a good bomb. Because if it were a bad bomb, we had this situation. The possibility of D2 clicking is 0. It could not have clicked. But now since we have a click, which means that still the photon has not been absorbed, but the bomb exists, it's inside the path, and D2 clicks, has clicked, which means that there must be a bomb, and the bomb is a good bomb. So now we have detected the presence of a good bomb without any photon interacting with the bomb. How do we know that the photon has not interacted with the bomb? Because the photon has survived all the length of the interferometer and been registered at the output port. So it has not interacted with the bomb inside the interferometer. Otherwise, it would have not been able to come all the way out and hit the detector. So this means that we have detected the presence of a good bomb without a photon interacting with it. We have looked at something existing in a region of space without actually looking at it. Yes, please.
Sir, pathwise आप explain कर सकते हैं D2 का D2 के click होने की explanation, because if it's taking path 1, then it makes sense. But what if it takes path 2? और हमने पिछले वाले में ये भी तो discuss किया था कि D2 जो है वो नहीं होता, it cannot be. So how all of a sudden why is it clicking now? वो तो होता ही नहीं था.
All right, so this is the counterfactual part of this experiment. So D2 was not clicking in this scenario. Why was it not clicking? It was not clicking because we did not know which path the photon has taken. Right? So there was some wave that existed here, some superposition that existed here, and the superposition was such that this gave us destructive interference here. Now that condition for destructive interference has kind of gone away. That means that this detector is now clicking with a finite probability. And now if this, by the way, if detector D2 clicks, can we tell which path the photon has taken? Yes. We can now tell which path the photon has taken. It has taken this path, path number 2. It has taken this path because if it were to take path 1, it would have interacted with the good bomb and exploded it. But this path is only taken when a good bomb exists inside this path. So this is the counterintuitive, the non-commonsensical part of this experiment. Yes, please.
Sir, I don't get the last part. How do we conclude it's a good bomb if D2 clicks?
All right. So right. So that's the kind of drama of this. That's actually the interaction-free part. So suppose this were a bad bomb. There are two possibilities. A bomb exists. Agreed. What kind of bombs do we have? Good and bad. So if this were a bad bomb, then the single photon would have gone through this, would have taken the entire superposition. It would not have interacted with this object, and the superposition would remain intact. And when the superposition remains intact, and we know the interferometer is balanced, we know that detector D1 can never click. So with a bad bomb, D1 never clicks. Oh, sorry, D2 never clicks. With a bad bomb, D2 never clicks. So if D2 clicks, isn't this logical that the bomb cannot be a bad bomb? It must be a good bomb. Yes, please.
Sir, isn't there a chance that bomb could explode ho jaye?
If the bomb explodes, neither of the detector can click, because a bomb explosion means that a photon has interacted with the bomb, it has triggered the bomb, and it's a destructive process, which means when the photon has given off all its energy to the bomb, it has been annihilated. Right. So this happens with a 25% probability, but whenever this happens, we have detected the presence of a good bomb without interacting with it. All right. Yes, Mohammed, you had a question?
Sir, clarify.
Yes, please.
My question is कि जो interference होती है, is that of the electromagnetic wave या the probability distribution?
So interference is the superposition. Remember in our quantum progression kind of argument. So let's see how the quantum state progresses. We start off with 0. Now, first of all, try to remove your fixation to the word interference in the nominal sense of the word. You start off with state ket 0. The first beam splitter BS1 or B1 produces, say, a superposition. The first beam splitter creates this superposition. Then the two mirrors just swap the ket 0 and the ket 1, they just change their direction. So ket 0 becomes ket 1 becomes ket 0, and that's it. So I'm just going to leave out that step. What the second beam splitter does, out of this ket 0, so I've now written down this coefficient 1 over under root 2, out of this ket 0, it creates another superposition. Whereas this, when it interacts with the beam splitter, creates another superposition. Now it happens that there's a minus sign here. What this means is that this path interferes with this kind of term destructively and just washes away this part. So only one of the channels, by the way, there's another 1 over under root 2 here. Only kind of. So this produces this. There's a 1 over under root 2 here and a 1 over under root 2 here. So I'm left with ket 0 here. So only one of the output channels gives you a click. You do not have a ket 1 here. Only one of the output ports is occupied. So this is what I mean by interference. Yes, please.
So why is there a minus sign there?
Yeah, I've explained this many times.
I wasn't present for the
So be present in class. I've explained this about 3 or 4 times, by the way.
relevant to this lecture.
So that's the action of a beam splitter. What the beam splitter does, it creates a superposition. So one way in which the beam splitter can work so if a photon comes in this through this path, this beam splitter has two input ports. One is the photon could come in through this path. The other possibility is that the photon can come in through this path. I call this input channel ket 0 and I call this input channel ket 1. All right. There are two possible output ports. Let's call this channel ket 0. Let's call this channel ket 1. I could also give them other labels, ket 3, ket 4. Now what happens is that the photon coming in through this path creates a superposition of both of these output ports, and that superposition is ket 0 plus ket 1. If it comes in through this state, it creates ket 0 minus 1. And this happens because the beam splitter has been engineered in this fashion, has been made in this fashion. If you knew a little bit more about quantum mechanics, I could say that the beam splitter does a unitary transformation, and for a unitary transformation, it's important that it takes up these forms. So it's an implication of unitarity. You can just imagine that the beam splitter is made in this fashion. Whenever light sees a surface and is reflected, its phase changes. Depending on which direction the light comes and sees an object, whether it sees the silvered surface, its phase is going to change differently. If it sees the unsilvered region, it changes differently. Light is refracted from a surface. The transmitted wave and the reflected wave take up different phases. This is a phase that is engineered into the system. All right. So now let's one last question before I move on.
Explain the notation after its being predicted.
After it's been
After its being predicted.
this part. So ket 0 transforms to this part, 0 plus 1 over under root 2. Ket 1 transforms to this part. So do you understand this notation? So that's what this beam splitter does. It creates a superposition of these two quantum states. I think you should come and talk to me in the office hours or see the TAs, right? If there are further confusions. Any more questions, by the way? Anyone else? Yes, please. For this? Well, it does have practical. Suppose this were an atom. This were not a classical bomb. This were an atom, and you wanted to find the state of this atom, and you wanted to preserve your photons because they're expensive. So you can look at the state of this atom or measure the state of this atom without the photons being absorbed. So now let's in this, by the way, excuse me, let's take this concept a little bit further. If you want to detect the presence of a good bomb in an interaction free manner, does D1 clicking does the D1 click tell you anything? No, it does not. It's just inconclusive. All right, because if D1 clicks, the bomb could be bad. Then this scenario is similar to scenario number 1 of a balanced interferometer with no obstruction placed in it. And if this detector clicks, since it remains a balanced interferometer, it could also be a good interferometer, a good bomb, because why could it be a good bomb? Because the photon has not been absorbed, there is no explosion. So it could still be a good bomb. And now you know that the photon has taken path number 2, the which path information has collapsed. So these are two kind of realizations, but you can't tell whether it's a bad bomb or a good bomb. So D1 does not tell you anything. So do we really need the detector D1 here? We can just let away with it because it doesn't give you anything extra. All right. So it's possible that I just remove this detector, and if still so then I have two scenarios. I have a scenario that detector D2 does not click and a scenario that detector D2 clicks. But then it's also possible that this kind of photon, I can connect this output channel with the input back again. Let's try doing that. Let's try to recycle the photons. It's a slightly more advanced version of a no interaction or an interaction free memory. Let's try to recycle the photons. By the way, in this example, in this thought experiment, if I were to define a success probability, let's call it kind of eta. A success probability that we find the detection of a good bomb in an interaction free measure, in an interaction free scenario. So the probability that an interaction free measurement takes place is 1/4. So this is a kind of an efficiency of a measurement, right? So in 25% of the cases, I can detect the presence of a good bomb without interacting with it. Got it? Now let's see if we can increase this a little bit. Can we increase this efficiency of measurement? So this is kind of stuck at 1/4. We can only, now we moved away from the classical world in which we had zero probability, zero likelihood of detecting the presence of a good bomb without exploding it. Now with quantum mechanics has given us some headway. It has given us some leeway. Now we can detect the presence of a good bomb with 25% probability. So at least there's some improvement. But can we make it go higher? So now if I were to take this interferometer and I just had this detector D2 here, just this detector D2, and of course I had my bomb as well. Now suppose I were to take kind of this photon, I would put an optical fiber, and the optical fiber takes this photon and puts it back here. This is my optic fiber. What an optical fiber does is a conductor for photons. It just is a channel for photons. Got it? So now I have this scenario. So now I shine in an initial seed photon, ket 0. One seed photon comes into this interferometer and it starts the experiment. Now there's a now what's going to happen is in the first run, which means if one photon has been shown into the system, the bomb can explode with the probability 1/2, then it's a good bomb. Okay, but that does not give you an interaction free measurement. It's not interesting. If detector D2 clicks, which happens with 1/4 probability, then it's a good bomb. You know that straight away. But that's happening with 1/4 of the probability. All right. Now suppose neither detector D2 clicks, nor does the bomb explode. Is the bomb a good bomb or a bad bomb? Could be either. This is this scenario here. It could be a good bomb and it could be a bad bomb. But now the photon has not been absorbed. It's still there somewhere in the system. Where is it going? It must enter this optic fiber. It has to go somewhere. So it enters the optic fiber and then is recycled into the input port, and the experiment repeats itself. The photon is now being recycled. So in the first case, the probability, so in the first round, the probability in the first round that if neither the detector clicks nor the bomb explodes, the probability for this happening is 1/4 in the first round. So this is no explosion and D2 is silent, right, in the first round. Yes, please. So 1 degree of freedom is the path the photon takes, but now we're doing the experiment in successive time bins, which means the photon travels with a finite speed, with the speed of light. So this interferometer has a size. So the second photon, the second run of the photon will be available after some time delay, given by the speed of light. So you can break up the experiment into time bins. Okay, got it? So now in the second round of the photon, it might take a few nanoseconds for for the same recycled photon to enter the system. Now in the first round, no explosion and D2 remaining silent has a probability 1 by 4. All right. Now what's the probability that no explosion happens and the D2 remains silent in the second round as well? It's 1 by 4 into 1 by 4. It's 1/4 of 1 by 4. Got it? So the probability that no explosion and D2 remains silent in the second round is 1 by 4 into 1 by 4. And if this keeps on happening, if after n rounds you still do not see the detector D2 clicking, and you still have not received an explosion, what's the probability of this scenario in n rounds? It's kind of 0. Your physicists, your mathematicians don't say 0. You really need to add 1 by 4 plus 1 by 4 squared plus 1 by 4 cube, correct? All the way 1 by 4 n, right? Right. So now what's the probability that if you repeat this experiment for an indefinite period of time and the bomb does not explode and D2 has never clicked? 1 by 3. So you take the kind of infinite sum of this series, right? So you now have a geometric series and you form this sum. This is going to be 1 by 3. So now there's a 1/3 probability that this is a good bomb and a 1/3 probability that this is a bad bomb if in a run of experiments, in a long sequence of experiments, the detector D2 has never clicked and neither has there been an explosion. So now we've increased this probability from 25% to 33% with the help of photon recycling. By the way, you can increase it to 50% by using beam splitters that have a slightly different value of reflectivity versus transmissivity. Anyway, I'll just not going to brood upon that point. So any questions here? Yes, please. It represents the probability that there is no explosion and the D2 detector has never clicked in a long run of experiments. So there's still a probability that this is a good bomb and a probability that this is a bad bomb. But the probability that it's a good bomb is 1 by 3 now. Yes, please. Unchi bole?
If it does ever enter the optic fiber, that would mean that it would never go to detector 2. So what are
Why? Because if it enters the optic fiber, you're still issuing the photon into the interferometer. So when it reaches here and the two paths recombine, it still has a likelihood of entering D2.
So if it enters D2, it wouldn't enter the optic fiber.
Right. If it D2 clicks, then the experiment is shut. The photon has kind of been destroyed. So you need to enter a new photon. It's not a recycled photon that's going to come in. Yes, please. All right. So now what we would like to do is, so what we've seen here so far is that quantum mechanics, simple understanding of quantum states, superpositions, a simple understanding of interference can give you these counterfactual experimental results which are totally explainable, explicable. They can be explained by theory. All right. So now let's do some other twists now. I would like to talk a little bit more about quantum inference, so that your kind of questions are also answered in a satisfactory fashion. Now, I need your 10 minutes of close attention, because is our quantum system, can we call it a qubit? Is it a qubit? A quantum bit? Why not? It is a quantum bit. It's a 2-level quantum system, 2 degrees of freedom. It's a qubit. Any 2-level quantum system is a qubit. And you've also come across the word quantum computers. All right. So this interferometer is really a quantum computer. It's the simplest quantum computer you can think of. And I'm going to bring home this idea that we can build a simple quantum computer using a single photon. Now let's look at the interferometer again, the Mach-Zehnder interferometer. So a single photon comes into the state quantum 0, ket 0. We've already seen this balanced interferometer. Now let's suppose we change the scenario a little bit. Here we place an element. Let's place a small glass plate inside one of the arms. All right. Now what the glass plate does, it gives a phase to a particular quantum state. Now, which path is this glass plate placed in? Right, it's in the ket 1 path kind of thing, right? It's in the vertically going photon path. So it changes. So what this glass plate does, so ket 0, it does nothing to this path, to the ket 0 path. So we have this glass plate, let's call it a phase plate. It does nothing to this quantum state because it's oriented in such a fashion that it only sees this arm of the interferometer. So only a vertically going photon, not a vertically polarized photon because we're talking just about the path, only a photon that is vertically propagating sees the glass plate. So it does nothing to this path. However, if ket 1 sees this phase plate, it introduces a phase. It puts a complex number next to this quantum state. EI some phase phi. Phi is a real number, but EI phi is a complex number. All right. So now what I would like you to do is, on your notebooks, in the next 5 minutes, do a state progression calculation. So you're inputting a state ket 0, you know what the beam splitter does, you know what the phase plate does, you know what the mirror does, mirrors do. So this is the action of the phase plate. So let me rewind and tell you what the mirror does. So a mirror interconverts ket 1 and 0. This is what the mirror does. And any beam splitter does the following. All right, so in the next 5 minutes, we'll take a break after this calculation is over. Can you please calculate what the quantum state is going to be after the second beam splitter? Please take 5 minutes. No questions in the meantime, just calculate. All right, so gladly, some students have been able to kind of go through this calculation on their own. It's not very difficult. Let's see. Would you like to come to the blackboard and reproduce this? The student who just I talked to at the very end, would you like to come to the blackboard? नहीं वो हाँ आप आना चाहती हो? All right, so here is your input quantum state. The first beam splitter creates a superposition. Then the quantum state sees the two mirrors, mirror 1 and mirror 2. So these are, just be quiet please. So these are just probability amplitudes. 1 over under 2 is a complex number. It's being multiplied with this quantum state and with this quantum state. These are just, and we need this because the state needs to be normalized. So nothing happens to the probability amplitudes. Ket 0 goes to ket 1 and ket 1 goes to ket 0. All right, nothing that, and I can write them in any order I like. Now this entire superposition, still the superposition has not collapsed, and the superposition passes through a phase element. It's inside the interferometer and we are not prying open into the interferometer and not observing anything as yet. So this entire quantum state, this is a legitimate quantum state. This now progresses and sees the phase element. What the phase element does, so I'm just going to change the order a little bit. I'm going to write ket 0 before I write ket 1. Doesn't make any difference. Now with this ket 1, this is not the complete quantum state. This is just one term inside the quantum state. It accrues. I use this word accrues. It picks up, it gathers a phase factor EI phi. Is this a legitimate quantum state? Yes, because the probability amplitudes squared of each coefficient of each kind of sub component, you add them up, still gets you 1. So the quantum state remains a legitimate quantum state all the way through. Then what happens, I progress this quantum state through the second beam splitter. So the two kind of paths, even though I don't know which path the photon is taking, they now recombine and interfere at the second beam splitter. The second beam splitter does another interference experiment, and then I just kind of, what happens to this quantum state? It goes into 1 over under root 2 ket 0 plus 1 plus EI phi. Nothing happens to the probability amplitudes. And what happens to this quantum state? Once again you generate an interference kind of superposition, and then you kind of just do simple manipulation of these terms. You have 1/2 1 plus EI phi ket 0 plus 1/2 1 plus, sorry, 1 minus EI phi ket 1. Now I can do a little bit of further simplification as that student has done, but I'll leave it at here at this point. And now the question is, what's the probability that detector D1 clicks? If this were the ket 0 channel, if this were the ket 1 channel, what's the probability that ket 0 detector D1 clicks? Let's call this state the output state psi out. This is my output quantum state that has emerged from this quantum computer. Why do I call it a quantum computer? I'll explain later. But now with this quantum state, which is the output from the interferometer, what is the probability that detector D1 clicks? You find the inner product of this state with ket 0 and take the modulus square. Can you please do that for me? What's the result of this inner product? Ket 0 and ket 1 are orthogonal states. So what's the result of this? One over 1/2 brackets 1 plus, that's it, right? So I just, this term would survive, whereas this term is going to be washed away because the overlap of ket 1 with ket 0 is 0. So I'm just picking up, extracting one of the probability amplitudes. And now how do I find the probabilities from a probability amplitude? Modulus squared. So in order to find out the probability that the detector D1 clicks, I take this term here, psi out, which I found already, inner product with ket 0, and find out the modulus square of this term. Now how do I find out modulus square? I take this is a complex number, I multiply it with its complex conjugate, and the answer must now be real, because the probabilities have to be real. There is no concept of complex probabilities in normal quantum mechanics. So if I were to find out this result, how do I do that? I just take the modulus square of this, which means 1/4. I first write the entire term with all the phases inverse, which means the complex conjugate, which really means the complex conjugate of 1 is 1. The complex conjugate of this number is the same number with the minus sign over here, not a minus sign here. It's a minus sign over here. And I multiply this with the original number 1 plus EI phi. So it's the number multiplied with its complex conjugate. That's called the modulus square, and that gives me the probabilities. And this is due to Max Born, who said that we do not know what the probability amplitudes really mean, but that modulus square has a definite meaning. It's a probability. Probabilities are what you see in an experiment, right? So now if I calculate this probability 1/4, let me do it just once for you, and then you can do it on your own. 1 multiplied with all of this is 1 plus EI phi. E multiplied with all of this plus 1. So this is 1/4 2 plus 2 cosine of phi, right? So this thing, it's a trigonometric identity, is equal to 2 cosine of phi, right? And I think there are some homework problems which kind of, yeah. Right. So, and if I now kind of, is this a real number? Yes. So if I just change my orientation of the blackboard a little bit, this is 1/2 1 plus cosine phi. Now there's another trigonometric identity which kind of simplifies this even further. What's that? What's this? Can I rewrite this as something else? I can write this as cosine square of phi/2. So what's the probability that detector D2 clicks? You can do the entire calculation. Once again, replacing psi out, so and finding the overlap with ket 1, which is going to be all of this term here, this one, and then take the modulus square. You'll get something. In fact, that something will be 1 minus this sine square phi/2. So now after 10-minute break, we're going to kind of graphically plot and make sense of all of these results. So let's have a 10-minute break. हमें नहीं पता किस पाथ से जा रहा है फोटोन, नहीं टूटती क्योंकि the photon is not absorbed by the phase plate, it just imparts a phase difference. Alright, so let me kind of now interpret this experimental result and this mathematical result. What's happening here is you have an interferometer and I'll come to the question, this question posed by this experiment later. So you have a beam splitter here and a mirror here, beam splitter, and on one of the paths, either of the paths, it could be either of the paths by the way, I could have placed the phase path here as well. So now I have a phase plate in one of the paths, and this phase plate introduces a phase difference phi between the two paths. Normally this would be a balanced interferometer. If this were a balanced interferometer, interference would take place and one of the detector clicks. And now I have two detectors, and now I can tune the probability of detection on each of these detectors. So this is my D1, here is my D2. Here is the incoming photon. Probability that detector D1 clicks is cosine square phi by 2. The probability that detector D2 clicks is sine square phi by 2. Now remember, I'm talking about a single photon coming into the experiment. And when we want to find out what the probabilities really are in a measurement, we have to pass in multiple identical copies of photons so that we can build up these statistics. Is this clear to you? Is this clear? Any questions about this calculation? All right. The point is that with a single photon in one run is either detected on D1 or on D2, right? Therefore, in order to kind of verify that these are the real probabilities, you cannot rely on a single photon. You have to repeat the experiment with a multiple number of identically prepared photons so that these probabilities reveal themselves, just as a single coin toss cannot tell you what the probabilities are. Anyway, so this is an a priori probability as well, which means that if you were, even before you were to do a measurement, you could predict the probability that detector D1 is going to click, and that's going to be cosine square phi by 2, and D2 clicking is sine square phi by 2. Now if I were to make a plot, so this is my phi, what will PD1 look like? It's going to look like a cosine square curve. What is that curve? Can you draw it on your notebooks? A rough sketch. No, just first respond to my question. Anyone would like to raise his or her notebook to me? Yes, the same, the kind of form, but yeah, that's more like it. Right. So this is the cosine square phi by 2 is going to look something like this. So this is my probability of D1 clicking for a certain setting of the phase. So if I were to set the phase at this value, this is what the probability of detector D1 clicking is going to look like. And what's the probability, what's the waveform or the kind of probability that detector D2 clicks? It's going to be 1 minus this, which is just, it's going to look like this. So they are complementary to one another. If one detector clicks, the other doesn't, but if you build up the probabilities, now you can scan this phase. In a real experiment, you can change the phase. That phase can change either by changing the thickness of this plate, or there are some objects which are called electro-optic modulators. You change the voltage that is applied to this material and it changes the phase. So there are different kinds of mechanisms by which you can change the phase. If I were to place the phase plate here, over here, identical results would be achieved. But if I were to place identical phase plates in both of the paths, what's going to happen? If I were to kind of place an identical phase plate here, a totally identical phase plate here with the same value of the phase, will I get, now remember, now kind of these are looking like interference fringes, aren't they? They are looking like interference fringes. So we are qualified, and it's a legitimate thing to say that this is an interferometer. So it is an interferometer. I hope that brings to kind of peace to your minds that why is this interference? This is an interferometer. And a single, that's why we call this an interferometer, because you can get these variations between bright and dark ports. All right, it's just like what you see on a screen. If you get to get interference patterns, you see bright fringes, dark fringes. The same kind of argument is appearing here. Now, if identical phase plates were placed, what's going to happen? Would I see an interference fringe? Then I would recover the original balanced interferometer. No interference fringes will appear, and I will just get one of the detectors to click. No interference is going to happen, because what this phase plate does, it breaks the indistinguishability of the paths. Let me write this down and then I'll explain this. A phase plate in one of the arms, so I'm going to erase this kind of. So now I'm going to talk just about a single phase plate. What the phase plate really does, it breaks the indistinguishability of the paths. The phase plate breaks the indistinguishability of the two paths. Why do we see interference? We see interference because we have no which path information. We cannot tell one path from the other. Correct? Which means that the two paths are indistinguishable. They are the same. If the two paths are exactly the same, they are of the same length, there is no uniqueness of one path over the other, then we see interference pattern, because then we cannot tell which path the photon has taken. What the phase plate does, if it's placed in one of the paths, one path becomes different from the other. It becomes distinguishable from the other. So now we have broken the indistinguishability, which really means that one path is now distinguished from the other. You can discern one path from the other. They are not the same any longer. And that's why interference pattern disappears. So the role of the phase plate is to break the distinguishability. Now with the help of the phase plate, we can get varying degrees of which path information. Right? We can get varying degrees of which path information. And we can shift the output from this detector to this detector. If this phase were, say, kind of, if this were pi, if the phase were pi, if the phase were 0, only detector D1 clicks. That's the kind of balanced interferometer we've been talking about. Phase 0 means really the phase plate is as good as it doesn't exist. It has no impact on the photon's quantum state. If, however, this phase is pi, if this phase value becomes equal to pi, then we are here. When we are here, the probability that detector D1 clicks turns down to 0. and the probability that detector D2 clicks goes up to 1. The photon must be somewhere. So if this probability is 0, at the same setting of the phase, this probability must be 1. In between, you have scenarios that are in between. So we can shift the output from this channel to this channel. We could have, in this case, we could have ket 0 coming in, ket 1 going out. So this entire interferometer with this setting of the phase inverts ket 0, converts it to ket 1. If you were to input ket 1, it would make it go to ket 0. So all of this might act like a logic gate. It's a NOT gate, quantum NOT gate. And this is how you can build. So that's the big idea of quantum computers. Out of these elements, you can build logic gates, quantum logic gates. Out of those logic gates, you can build quantum circuits. Your workhorse are not the classical bits, now they are the qubits. And the kind of technology that we use here are photons. With the help of path of a photon, which becomes your information carrying physical element, you can do processing of that information. Ket 0 coming in, ket 1 going out. That's a simple example of a quantum gate, a quantum NOT gate to be very precise. And we'll have one full lecture on these quantum gates and quantum circuits. We'll try to build some kind of quantum algorithms out of this in just one lecture. So any questions about this? Yes, please.
Sir, once we have changed the phase to be phi, we know that the photon will emerge only in the ket 1 state. So हमें momentum के बारे में uncertainty has become 0. So are we now uncertain about which path it took, or?
So now we are certain about the path that it has taken, because then it must have taken this path, because it has developed a path, it has gone through this. That's why this detector is clicking all the time.
We're certain about both things. We're certain about the momentum as well, that it will come out in ket 1 state, and then we're certain about the path as well, that it will take this path.
So all right, so let me rephrase. So if this detector always clicks, I thought you were saying in between. If this detector always clicks, you are certain about the momentum.
Yes.
And you know nothing about the path. Because it's in this entire calculation, you know nothing about the path. So if this which path information is preserved, then if this which path information is not available to you, then the momentum is certain. Then only one of the detector is going to click all the time. So there are two extremes here. One extreme is that both of the detectors clicks with equal probability. When is that going to happen? That is going to happen when phi is equal to pi by 2. When phi equals pi by 2, you are at this scenario, kind of here. In fact, I haven't drawn it properly. This has to be 0.707. So at in between, you have this value to be equal to 0.707, 1 over under root 2, actually 0.5, sorry, 0.5, which is the square of 1 over under root 2. So at pi equals 45 degrees, you have complete uncertainty about the momentum. And when that is the case, complete uncertainty about the momentum, only then can you say that you know which path the photon has taken.
Took the path, the one that has the phase. Okay.
Otherwise, it's in between.
My question is, if phi is equal to 0, then we don't know which path it took, but we know that it
And with phi equals pi, we don't know which path it has taken.
how? I mean,
So why with phi equals pi? Because phi equals 0 and phi equals pi, they are kind of, since quantum mechanics deals with the modulus square, so if you take a negative minus 1 and square it, it's going to be the same as 0 modulus squared. So that's why there is no distinguishability between 0 and pi. All right? And it's also because this is a spin half particle or it's a qubit. So and when I talk about Bloch spheres, if I ever get the chance to talk about the Bloch spheres, if you take a pi rotation on a Bloch sphere, it does not change the probabilities. It's like a kind of a global phase. A slightly more technical answer to this, but you should rest assured that, yes, please.
Sir, at pi by 2, shouldn't we assume that it's in superposition कि दोनों जगहों पे है? Because it's not favoring one for the other. और momentum है तो किधर से आ रहा है? ये मतलब we're saying that the momentum it makes it. Wait, how do I phrase this? So we're saying that that the momentum is completely uncertain, so the path has to be certain. लेकिन y over here जब दोनों एक होते हैं, वो तो peak पे नहीं होना चाहिए या trough पे नहीं होना चाहिए.
So what happens is, if this is pi by 2,
Yes.
if this is pi by 2, you put pi by 2 here, ei pi by 2, you get iota, and then work out the results and find out the two probabilities. You will see that they turn out to be the same. All right. So I think it's worth putting in pi by 2 over here. The key point is that this phase element, if it's not 0 or pi, it's going to make the paths lose their indistinguishability to varying degrees. All right. So that's the key argument here. Any more questions? Yes, please.
Sir, if the phase state is at pi, so it's always going to click d2, right? So what if the photon actually takes the other path? Can we not count for that at all?
We can't say which path the photon has taken. We don't know which path the photon has taken. That's what we've been trying to argue.
Like, if the phase state is inserted in there, we're going to assume it always takes that path, which is why it's
No, we don't know which path the photon has taken. It's really that see, the whole point of this is, if either of the detector clicks, and it always clicks, say D1 always clicks, we don't know which path the photon has taken. If D2 always clicks, we still don't know which path the photon has taken. If in multiple runs of the experiments, sometimes D1 clicks, sometimes D2 clicks, there's some uncertainty about the momentum, which means we have some degree of information about the path. All right, so that's what it comes down to. So you can, it's possible to have partial information about the which path. The two extremes are when you either have no information about the which path or you have complete information about the which path. That happens when phi equals 0 or pi. Yes, please.
Sir, which path में हमारे पास तो दो ही तो options है. It can get 0 path or get 1 path. How can we have partial information on when there's only two options?
I mean, why not?
Because हमारे पास अगर थोड़ी सी भी information है तो we can infer which one it's taken. Because like ये कैसे हो सकता है कि we sort of know it's taken one and we तो if it's taken one, it's taken one. If it's taken 0, it's taken 0. What would partial information even mean?
Well, these are a kind of philosophical questions. I mean, really, there's no possible kind of clear-cut answer to this. So what happens is that these fringes can have reduced visibility as well, but that's something technical. So that it's possible that their bottom does not hit 0 and their maximum is not 1. So this is reduced visibility fringes. They correspond to partial information. So so when we talk about probabilities, if you say there's a probability that 75% of the time detector D1 clicks and 25% of the time detector D2 clicks, and if I ask you to question which path the photon has taken, what would your answer be?
75% of the time
No, that's impossible. Because in a single run of the experiment, you are getting these a priori possibilities. So what would your answer be about the information in this case if 75% of the time one detector clicks and 25% of the time, and it's just a single photon coming in? Right. So what happens is, if you were to talk about this from a thermodynamics perspective, the state has some entropy. The entropy is kind of the uncertainty. If the entropy is 0, you are certain about a particular thing. So the entropy could be between 0 and 1. It could be between 0 and a maximum value. All right, so it's slightly more advanced stuff, and I agree this is somewhat kind of interpretative. All right, so I think I should move on. One last question.
When phi equals to pi by 2, we're uncertain of the momentum. But due to the principle, we're certain which path to be taking. How is it logically to give which path? How are we certain of the momentum?
So if your phi is here, there's a 50% probability that this detector clicks. So we're uncertain about, in a single go, about the momentum. The momentum has become uncertain. Okay? Now you would like to ask, how do we know that which path? So we must know something about the path. The path, that in that case we can deduce that the photon has okay, so let me think of an answer to this. So then this becomes equal to EI when phi is pi by 2, EI pi by 2. So this becomes iota. Correct? Let's see. So I put in EI pi by 2, which is cosine pi by 2 plus iota sine pi by 2, and iota over here. All right. So when this happens, I get this, and here I would get iota, all right, so here I would get 0, 1 plus iota, here I would get 1 minus iota. All right, so let's see. G.
Why would we get an iota there? Get 0 plus iota get on the first one. Second one, yeah, I get the first one.
1 minute, 0 iota. आहा, यहाँ आयोटा आएगा, यहाँ आयोटा आया, cat 1, cat 1, 1 और 2. ठीक है? So now I have an answer to your question. किसने पूछा था question? All right, so let's pay attention here. I think this is going to solve many kind of queries. When the phase is phi by 2, 90 degrees, we're on this curve here, right? So this is, my phase is now pi by 2. So what I did in this calculation is, instead of EI phi, I just inserted the value of EI phi, which is iota. Now let's look at the progression of the quantum state. So this becomes 0 plus iota cat 1. This would become, so I just factor out this iota. This would transform into 0 minus 1. All right, so iota has been factored out. Now I take all the cat zeros in this expression and I kind of add their coefficients. So I have half here and I have iota here. All right. Then I look at what exists with cat 1. So here I have iota cat 1 and here I have minus iota cat 1. Correct? So what happens when I add the two terms? 0. This term just disappears. Got it? So when this term disappears, I'm just left with cat 0. So I do not have a superposition at the end. which means that I have collapsed the superposition after the beam splitter. Alright, so that's the answer to your question. In the other cases, I have finite probabilities at any other point. By the way, the same scenario would be achieved at phi equals 3 pi by 4, when the two probabilities are exactly equal. So the difference between the quantum output state here is now I have gotten rid of the superposition all in one go, and now I have certainty that only one of the detector is going to click at phi by 2.